Hello and welcome to Lecture 3 of the Motion in a Straight Line unit in Phys 1104. In this lecture we will finally make it properly to the idea of velocity. Before we go any further, I want some better data to work with. So here is a setup that you'll become familiar with in the lab. This is a cart on a low friction track, and over here is what we call a motion sensor, which is basically just a little sonar. So it's sending out pulses of sound and timing them to determine the distance to the cart, and the result is going to get graphed up here. And so you can think that essentially all it's doing is it's assuming there's a set of axes here, and it is just getting the x position of the cart as a function of time and graphing it for us. So here's the data. And you can hear the motion sensor clicking away, and I'll send the cart back in the other direction. And there's our data, which we can now look at more closely. We're ready to talk about velocity properly at last. So here is some x versus t data for the cart, and I've indicated a time interval, delta t, and an x component of displacement, delta x, that corresponds to that time interval. And because the cart was going in the same direction and in a straight line for that whole time interval, that delta x represents a distance traveled. And so we can use it to get an average speed, like so. Just take the delta x, the distance traveled, divided by the delta t, time taken. And that applies to this shaded time interval. But notice what we've done. If you compare that with the graph, that delta x represents the rise of the graph during that time interval. And the time interval itself is the run on the graph. So what we've just calculated is a slope. Now we already knew that there was a connection between speed and slope, but this is suggesting that the slope is the speed. Well, almost. We'll get back to that in a moment. But first let me look at how to get that speed a little better. I just read those off the graph, and that was pretty rough because my ability to read the graph precisely is pretty limited. I can do better because I got the data in a data analysis software, and I can use it to get a linear fit, which will give me a better estimate for that slope. So let's use that. Now I can do the same thing using the software to get the slope of this part over here. And note that it's negative. Well, that makes sense. The cart is going the other way, and so the delta x is negative because x is decreasing during that time interval. But notice I haven't called it an average speed. A speed, by definition, is a distance traveled divided by a time taken. And you cannot go a negative distance, so a speed must always be positive. So this is not a speed. Well, what is it? Well, remember that these delta x's are not just distances. They are, in fact, x components of a displacement vector. And that's why they're allowed to be positive or negative, because components of vectors can be positive or negative. And so what we've just calculated here is the component of a vector, the x component of the average velocity vector. Well, having realized that, what we see is that the slope of the x versus t graph, the x component of position versus time graph, is the x component of the velocity. What we've just seen is a key idea that you'll use over and over throughout the course, especially in the lab, and so I want to make sure you've got it. So here is a position versus time graph, and we're going to use it to get the x component of the velocity at t equals 1 second. So if you're doing this through Moodle, Moodle will now ask you this question. Otherwise, you should still try and answer this before you move on.